different types of chemical bonds. And as I said before, this should be here, but I know it may have been a while since some of you did chemistry, so let's just run through it, use the information that you might have to use when learning about human physiology. So when we're talking about bonds, chemical bonds, we're talking about what is attracting atoms and holding them together so that they function together as a single unit rather than as two atoms each doing their own thing. And remember, two or more atoms put together forms a molecule, and we're going to use the word molecule because if it's a compound, it's a molecule. So we're just sticking with the word molecule. Once we are bound to each other, then that molecule is more stable than either atom by itself. And the type of bond is kind of determined by how many electrons each atom has and that kind of determines where the electrons are. And so for these chemical bonds, sometimes we're going to be transferring electrons where we're totally giving them up, and other times we're going to be sharing them. And that's going to be determining our two major types of chemical bonds, ionic and covalent. And we also will be talking about hydrogen bonds as well, because they are super important in the human body. So first we need to define what an ion is. And an ion is one that is no longer neutral. So we talked before about atoms being neutral, where they have the same number of protons as they did electrons. The number of neutrons doesn't matter. It's just the positive charges have to equal the negative charges. Okay. Now, if an atom loses an electron, it's not going to be neutral. And if an atom gains an electron, it's not going to be neutral. So if we look at this one, which now has more electrons than it does protons, that means it's going to be negatively charged. And compare it to this third one, which is showing it has less electrons than it does protons, meaning it's going to be more positively charged. So those are our two types of ions, either positively charged, okay? And there's a couple of ways that this can happen. But we have words that are used. Instead of having to write out positively charged molecule, negatively charged molecule, we have single words that can do that. When a neutral atom loses an electron and becomes positively charged, we call it a cation. Okay, so in other words, it's going to have more protons than it has electrons, and that is because it's lost one or more of its electrons. So just think of kitty cats. It's positively charged. Cats make you happy, okay? So just think about it that way. And that's in contrast to an anion, which is a negatively charged ion, meaning it has more electrons than protons, and this is because it's usually picked up some electrons. So it's very negatively charged, okay? So yeah, an anion. You don't like anions because they're negatively charged. All right. Moving on, let's go back and review those energy shells again. Remember, the innermost shell holds a maximum of 2 electrons. The second shell holds 8 electrons. And notice they're usually in groups of 2 after the first shell. The first shell, they're going to be on opposite sides. And the second shell, they're going to be shown in quadrants, 2, 2, 2, 2. And the third shell is also going to be in the same. So in other words, among the first 3 shells, we're going to have 2 + 8 + 8, or 18 possible electrons that could be there. Now, what is interesting about these shells is as you go outward, each shell has a higher energy level than the one inside of it. So you would think, oh, electrons want to be on the outside where all the energy is, but they have to occupy the lowest energy shell that's available to them. So the 2 has to be filled up first. Then the second shell has to have 8 filled up before you can start into the third shell. Now, atoms are going to be most stable when their shell is completely full. So it can be an atom that only has 2 electrons. That first shell would be full. Or it can be an atom that has 10 electrons, because then the first two shells would be full. Or it can be, as this one is shown, with 18 electrons, because the first three shells are full. And that makes it super stable. And these exist in nature. And because they're so stable, they're not looking around to combine with other atoms. However, most of our elements do not have full shells. Okay, most of them have a partially filled outer shell. So it could be an atom that only has one electron, or it could be an atom that has 3 or 4 or 5 or 6 or 7 electrons, or it could be one that has 11 or 12 or 13, 14, 15 or 16 or 17 electrons. All of those are less stable because they all have an outer shell that's only partially filled. Now, these atoms, they want to have outer shells filled. So they will, if they have one extra, they'll get rid of it, they'll donate it because they're kumbaya. Like, for instance, if they have 3 electrons, they get rid of one, then they only have 2, and they're out, and then their shell is full and they're very happy. Or if they only need one, maybe they will steal it from someplace. Like, for instance, if they have 9 electrons, they only need one more to have a full second shell. So they'll steal it from someplace. And sometimes they'll actually share electrons to fill the vacancies. Because if you think about carbon for a second, remember I said carbon has 6 electrons, so it has 2 in the first shell, and there's only 4 in the second shell. It's looking for 4 electrons. Okay, nobody's going to donate 4 electrons to it, so it's going to have a much better luck by sharing to fill its second ring. Okay, now whether they donate, they steal, or they share electron, that determines what type of bond is going on. So the first type of bond is called an ionic bond, where an atom is transferring an electron to another one. Because, for instance, sodium has a positive charge, it's got 1 extra 1, and it's going to chloride, which only has 17 electrons, and it wants that third shell to be full at 18, so it donates 1 to them. And so then it's very happy. So the atom receiving the electron becomes negatively charged. So chloride has a negative charge. Sodium has given up an electron, so it becomes positively charged. And opposites attract, the positive and the negative attract each other, and they form an ionic bond. And so this is showing what it is. Sodium giving up. Sodium has 11 electrons, so it's giving up 1. So now sodium will have 2 shells full, and now chloride will have 18 electrons, so it will have 3 shells full, and they're very happy with each other. Okay. And these ionic bonds are very strong. So this is showing the 10 that sodium is left with after donating. There is the 11th one. And this shows chloride was short 1, and now sodium gave it its 1, and so they both have outer shells that are full. Sodium chloride, that's your table salt. And as we know, we can pour table salt and let it sit on the floor, and they'll still be there years later. Very stable ionic bond. The next type of bond is called a covalent bonding. And what happens here is we're going to have 2 atoms, both of which have electron shells that aren't full, but instead of donating or taking, they're going to share electrons. Okay? And so hydrogen only has 1 electron, and as we said, chloride has 1. And so what they're going to do is they are going to share electrons. Okay, so this is not hydrogen chloride over here. These are different molecules. Apologize for that. And so what they are going to is this is showing 2 that in, whether this is indicating the second or third ring, that has 7, and so they're going to share, because this way they still have 6. There's the 7th of one being shared. There's the 7th of the other being shared. Okay, and so that's going to give us 1 bond with 1 electron from each atom shared with the other one. And it can just be 2 atoms together, or it could be, for instance, this carbon is going to form single bonds with 4 different hydrogens, because it has 4 of its own, but it's going to share it has 6 electrons, so it has 4 of its own in the second shell. Hydrogen has 1 in its first shell, and so they're going to share these 2. So they both will be there and share here and share here and share there. So each hydrogen is full because each hydrogen is sharing 1 with carbon, and the carbon is also full because it's sharing 1 with 4 different hydrogens. Now, in addition to these single bonds, we can have double bond covalent bonds where atoms are going to share 2 pairs. Like for instance, if we have 2 oxygen molecules. So what we said is oxygen has a total of 8 electrons. So it has 2 in the first shell and 6 in the second shell. And so the 2 oxygens each can share 2 electrons. Just sharing 1 would just give 7 in each outer shell. And so by sharing 2, now they have 8 in each outer shell. And if we look in biology in your body, most of our bonds are going to be these covalent bonds. Okay, not quite as strong as an ionic bond. When we look at covalent bonds, we can describe them as either being polar or non-polar. If they are equally sharing, such as we saw here in this carbon or these oxygens, then we say it's not polar. But and the same thing if 2 hydrogens are sharing. But in polar bonds comes in to play a lot with hydrogen and oxygen. Okay. The electrons are shared, yes, so that their shells are full, but they're not shared completely because if we look at hydrogen, it's just got a little touch of positivity in it. And oxygen still has a little touch of negativity. So just because it's like, it's a little bit pregnant. Okay, I know you can't be a little bit pregnant, you're either pregnant or you're not pregnant. But think of it this way, we have a little bit of positivity versus a little bit of negativity going on. And so when we look at water molecules, and we're going to have another oxygen, it's also going to have a polar covalent bond. And this is why the hydrogens are often angles, they are not completely on the 2 sides. So that brings us to another term, amphipathic. An amphipathic molecule is one that has both an area that is polar and an area that is not polar. And so this is what like soaps are that you use at home, and we will learn this semester. We have things called micelles and liposomes, and then also our phospholipid membrane is amphipathic. If we look at our phospholipid membrane, it has heads which are charged, and tails, fatty acid tails, which are not charged. So this part is not polar, and the head is polar. It's this phosphate group that you see right here in green. Okay? And so it's an amphipathic molecule. So in other words, if you drop this in water, only the heads like water. And you know, your body is a watery environment. So what happens is when you throw this phospholipid membrane into the watery environment of your body, what happens is it spontaneously forms this phospholipid bilayer, so that the tails, which do not like water, are in the middle, and the heads, which do like water, are on the outside. So talking about covalent bonds, I mentioned before we can have single bonds, double bonds, and we also can have triple bonds. So single covalent bonds, they're sharing 1 valence of electrons, so that bond is long, makes it very weak. By comparison to that, a double covalent bond, like we see in oxygen, they're going to share 2 pairs. It's going to be stronger. And then ones that have triple bonds, like cyanide, it's really hard to break. These are the strongest bonds because they are triple bonded. So let's go back and look at carbon again. As I told you, carbon has 6 electrons. So it has 2 in the first shell, only has 4 in the second shell. So it needs to have 4 bonds. Okay. And those bonds can form in a straight line of varying lengths. For instance, ethane is only 2 carbons and each has 4 bonds. 3 of the bonds are hydrogen and the 4th bond is between the 2 carbons. And compare that to propane gas, which is 3 carbon gas. So only the 2 on the 2 ends will have 3 hydrogen bonds, and the 1 in the middle only has 2 hydrogen bonds because the other 2 bonds are with the other 2 carbons. So that's one way you can have a straight chain. The other way you can have a straight chain with carbon is we can put in some double bonds in there. So in butane, we are on the end, we are taking away this hydrogen and making it form a double bond with this carbon. And so we got to get rid of 2 of the hydrogens because now each of these carbons has 4 bonds, and this is butane. And this is also a butane. And notice the only thing that's happened is we have changed where the double bond is, but chemically it's still the same number of carbons and the same number of hydrogens. Therefore, the name is exactly the same. It's just called 1-butene because the first carbon has a double bond here. This is called 2-butene because the second carbon has that. We don't need to know that in this class. I just want to explain to you why the names are the same. So that's how it works in a straight chain. But besides a straight chain, carbons can be in branch chains. And so what you do for a branch chain, you get rid of one of the hydrogens, and now you will have it bond to a carbon. And then that carbon will have 3 hydrogen bonds, or it will have its 4 bonds. And so basically, to branch it, you have to replace a hydrogen with a carbon, and then that carbon can continue on having more carbons branched to it, or just stop with the hydrogens next to it. And the third type of carbon skeleton is to form a ring. And when we look at the ring here on the left, you can see all the carbons, and you can count the 4 bonds with the hydrogens, and they can form a 6-sided ring with single bonds, or it can form a 6-sided ring with 3 double bonds. Now, this gets pretty messy looking, and so what you're going to see a lot is we get rid of the hydrogens and we just draw this structure, this 6-sided ring, and so every point is going to be the carbon, and then from the carbons you can just plug the little hydrogens coming off of it. And then this 6-sided ring is showing the location of these 3 double bonds. So you can understand that it has 3 less hydrogens than the other one did. All right. And if we do the same kind of abbreviation going back to the straight branches, it would just look zigzag where every point is a carbon, and we're just not putting the little hydrogens on it. And so we will see that shortly. But let's talk for a moment about hydrogen bonds, because if you remember, the hydrogen-oxygen bonding was askew. It was polar. And so when we look at water, it always looked like Mickey Mouse ears, with the ears being the hydrogens and the head being the oxygen. And so this end, the hydrogens have that little bit of positivity going on. So this side of the molecule is positive, and the oxygen is kind of negative down there. Okay, and so that negative oxygen, it's not a full -1 charge, it's a titch negative. It's going to be attracted to the slight positivity of a hydrogen ion. And so we are going to form a covalent bond that is extremely weak. And it's so weak that we don't usually just call it a covalent bond, we just call it a hydrogen bond. Because this way folks understand this is super weak. It's a covalent bond, but it is super weak. And so when we're looking at water, what we can see in this bottom one, you can see the positivity and negativity, and you can see that, yes, there's attraction from each of the positive hydrogen atoms, as well as attraction from the slightly negative oxygen. And so each water molecule can have multiple different hydrogen bonds, and this is going to lead it to us understanding some of the properties of water. So I put this upper right picture in here for you to realize that not only do we have these hydrogen bonds between different water molecules, but in the water molecule, there are covalent bonds between the oxygens and the hydrogens, okay? So we've got covalent bonds going on here, and we have very weak hydrogen bonds going on there. All right. So at this point, I've put 3 different types of bonds here. So it's time for you to stop and look at this, try to figure out what they are, ponder the meaning of the universe, think, oh, this is pretty straightforward. I've got this. Realize it's very straightforward right after you've heard it, but then practice again later on before it comes back to the test time. And when you're ready, you can restart this, and then you will see this slide. This next slide with the answers, but then I make it disappear really quick because that's the end of this tape. I'm going to stop sharing, and I want to thank you once again for all your hard work in this class, and I will see you again shortly with the 3rd step of the chemistry of life, which is now we're going to look all about water.